So in this session, we're going to look at some very commonly encountered continuous distributions, and they are commonly encountered uh, in your exams and your exercises and your intro stats lessons and homeworks and assignments. But they are there in your exam, in your homework assignments, also because in real life we tend to encounter them a lot. And in this particular session, we want to just dip our toes into these classes of distributions. So just a quick glance, we'll see uniform distribution, exponential distribution, normal distribution, and a bit related distributions that we'll also discuss more in later lessons will be student t distribution, chi-square distribution, and the F distribution. So these 6 classes of distributions, you ought to know them well, enough for you to be able to feel very comfortable with them, as comfortable as a dice distribution, right? We all know about throwing the dice. It's 6 numbers, all equal probabilities. So 1/6 for each phase. We're very comfortable with that, but I want you to be able to feel comfortable with these 6 distributions. Now, to begin, let's recall that all continuous distributions, all of them, are invented fantasies about the real world. In other words, in real world, they cannot be observed at all. All measurements, all observations are done through instruments, whether it's scientific instruments or our eyes, or our senses, our feel, and then we write down a quantity. And to the extent that when we write down, it will not be infinite decimal places. It will always stop at some point. So you see, it's almost a must that we are living in a discrete world. However, as we also start off this lesson series, talking about why it is very useful to understand continuous distributions. So while they are invented mathematical fantasies about real life, they are close enough, and they are often also supported by domain logic. That means when we apply them, the understanding of the science and the why behind those applications makes sense to justify these continuous distributions. That's why we have to understand the application areas a lot more in order for us to reverse. That means we look at a particular situation and then realize that we have to use, for example, uniform distribution. We look at a particular situation and we say, oh no, this is the time when we should be using normal distribution. We look at a given situation and say, nope, that doesn't make sense for us to use normal distribution. We should be using exponential distribution. So I'd like you to achieve that. Okay, so in other words, we're going from column 3 to column 1. Normal textbooks will introduce what is uniform, and here are the application areas. So it's like going from column 1 to column 3. I'd like you to think from 3 to 1, because this is what you will be encountering in your exams, in your real life projects, where no one is going to tell you what to do, and you will say, well, from my practice, it seems to be that it should be more suitably modeled by a uniform distribution. That is the kind of intuition I'd like you to have, right? Going from column 3 to column 1. Now, of course, along the way, we have to get familiar with some of the formulas here. If you can know them all, that's great. If you use it so frequently enough that you just somehow already memorize them, excellent. If you cannot remember any of them at all and you have to rely on tables, totally fine. Totally fine. All right. Very, very important goal that I hope you can get is go from column 3 to column 1. So someone tells you a story describing a scenario, and you're able to say, okay, this means that I should be, or the question is hinting to me to use uniform, not exponential, not normal. Yeah. So how to distinguish them, right? All right. So let's begin with uniform distribution. most values within are equally likely to occur. So we'll use words like equally likely. So for example, in a question, one might say, John estimates that the time of travel from his home to office will be equally likely from 25 minutes to 45 minutes. Yeah, okay, so here is the hint. Equally likely, isn't it? The question already told you. But the question will not tell you that it follows not uniform distribution. It has already hinted so clearly to you if you are looking at it, right? If you just miss the words equally likely, okay, let me use bell shape to model because everything is bell shape. No, and this is what you're learning here. Yeah, this is what you're learning here. Not everything is well modeled by bell curve. What happens if I forcefully use a wrong distribution or an inappropriate distribution to model the given situation? Well, you will still get the PDF, you will still get the probabilities, except it's all distorted. Yeah. What is not likely in your calculation becomes very likely, and then you act on it, and then you get the wrong answers or some damages in real life. Yeah. So you have to use the appropriate distribution. When when the probabilities are equally likely to occur, right? Like I'm not sure, but they seem all equally likely to occur. Or we have no knowledge at all. John doesn't really know how long he takes to go from his office to go from his office back home. All right, he doesn't really know. He estimates it ranges from 25 minutes to 45 minutes. He doesn't really know. They didn't say equally likely. So what should we do? That's right, still uniform distribution. Because recall from our discrete case that we apply uniform discrete distributions to cases where we know that they are all equally likely, or we have no idea about the probabilities. We have no idea. We don't even have enough information to say they are equally likely. Then, as a matter of unbiased kind of wisdom, we'll say they are equally likely. We are kind of going to make an assumption that they are equally likely. So either we know for sure they're equally likely, or we have no idea at all how probable they are, then we use uniform distribution. Does it make sense? Okay, so look for those words. And here for a practical purpose, we sometimes also use uniform distribution to model short intervals of what seems to be a complicated distribution. So for example, this one, right? It's neither bell-shaped nor chi-square nor F distribution or nor what because of some distortions here and there. But if we are interested in just this segment of the x values, then it is probably just good to assume it is uniform distribution, right? So it is a plateau there, a little bit off, is not by off by too much, right? So we are able to accept this simplification. And finally, in simulations, in computer generated simulations, and that includes computer aided design, computer aided engineering, games, all sorts of games, visualizations, movies, Hollywood movies, and computer generated characters. All simulations have to involve uniform distributions, right? So this is a very, very powerful use. In cryptography as well, a random generation of keys and passwords so that it is the hardest for a potential hacker to hack into also involves uniform distribution. In fact, the a test of how solid a cryptography algorithm, a proposed algorithm to encrypt information, is to see whether you can have a very uniform distribution of the encrypted um, bytes or data. Because if it is so uniform, then I cannot detect any congregation of letters or numbers and then be able to reverse engineer out what information you had before encryption. So as uniform as possible, means as um, hard to decrypt as possible. And that is kind of also a very important area of study involving uniform distribution. But that's just to let you know that its application is very wide, much wider than you think in terms of a continuous version of a dice. Yeah, okay. Now, the three very important functions or formulas. What is the height? What is the PDF? Yeah, so it's 1 over b minus a. This you should remember, I hope, because if the length is a to b, so the width has to be b minus a, and the overall area has to be 1. So what's the height? It has to be 1 divided by b minus a. So the height must be this, so that when the height multiplies by the width, we get an exact 1. That's the reason. So using the integration calculation or otherwise, you can get expected value of x is half of a plus b. Variance of x is half of b minus a squared. So over continuous space, they all look very nice. The formulas look very, very simple compared with the discrete version. If I may just flip back a little bit, the discrete version of uniform distribution, you can see this little extra plus 1 here, this little extra plus 2 in one of the copies of b minus a. Yeah, and these are just the ugliness when you have to go down to counting. Yeah, because you have to include the first one. If you do the n minus the beginning, you lose out 1, right? And 1 in a discrete space is 1. That's very important to account for, right? But in the continuous arena, the mathematics go a little bit easier actually. So we are able to uh, get a very beautiful b minus a square, and the plus 2 disappears because of continuous axis. Okay, so let's flip back to our continuous probability distributions. So over here. All right, so that's for uniform distribution, right?